In the last video, we talked about how to solve the path integral for the harmonic oscillator. But what if we promote that strategy to fields? How can we solve the path integral for quantum fields instead of quantum particles? Here's how. So recall how before we wanted to find the probability that a particle propagates from point A to point B. And that probability amplitude looks like this over here. And then what we could do was we could just break this middle part, this evolution term, into multiple time slices. So e times IH times n, and then times a, and then we inserted a bunch of completeness relations as well. And by doing that, we would arrive at the path integral for particles, which looks like this. And so this will give us the probability amplitude for the propagator. We're going to do the same thing for quantum field, but something get a little bit different. So first of all, we have to talk about what are called field states. So the quantum field is an operator that acts on some state, let's call it phi, and it gives us some eigenvalue times the state phi. So we define the field state as a state where it's acted upon by the quantum operator, the quantum field operator, and it outputs the classical quantum field as an eigenvalue times the same state. Where this classical quantum field is a quantum field that's not like an operator, that's not quantized. So for example, our quantum field could act on the state phi A and give us out phi of A mu times phi A, where this is the classical field that's evaluated at A mu. So by introducing this sort of quantum field state formalism, we are able to describe fields at like a particular range of positions. So just like how we could ask the probability amplitude that a particle goes from point A to point B, we can try to calculate the probability amplitude that a field state goes from phi1 to phi2, for example. And that's going to look like this over here, where phi1, again, the field operator will act on phi1 and give us a phi of x mu or x1 mu, or just like x1 if you want to, or or x1 is like contains t, x, y, and z, and then acting on the same state, and then phi2 is defined like this over here. So this kind of boils down to really asking for the probability that the field evolves from phi equals phi1 to phi equals phi2, because these field eigenstates represent particular configurations of fields, just like how the position eigenstates represented particular configurations of positions. So by using the same arguments as before, you can time slice the Hamiltonian, you can time slice the time into multiple pieces, and then we can arrive at what's called the field integral that looks like this. So where phi is a function of x mu. And this will give us the probability for this propagator over here, the chance that the field evolves from phi1 to phi2. So for the path integral, we looked at the probability amplitude that a particle goes from point A to point B by pretty much looking at all the possible paths that the particle can take between point A and point B. But for the field integral, we look at the field at phi equals phi1 and the field at phi equals phi2, and we look at all the possible configurations that can connect the fields at those points. So let's say here's the field at phi1, here's the field at like phi2, and we look at all the possible evolutions between phi1 and phi2, and we just like summed them all together. So the fields become the paths in a way. Now the field integral by itself is not a very useful integral in quantum field theory, because we don't really want to calculate the probability amplitude that fields evolve from some particular configuration, because the fields aren't really observables, right? Fields are just mathematical tools. The actual things that we observe are particles, energies, momenta, positions, things like that. A better thing to calculate in quantum field theory would be the path integral, but for an action with a source term of e to the I times s plus the integral over position j phi, where j is just some function of x, mu, and we call this a source. And this source doesn't really have a physical meaning. It's not an interaction term, but we can use this new sort of thing. We call it the generating functional zj, and we can use this functional to actually calculate the probability that two particles scatter in quantum field theory. And that's because this quantity over here, we call this the endpoint correlation functions. This quantity here is actually proportional to the probability that two particles scatter off each other. And we can find this quantity over here by using this functional over here. And we're going to actually show that in this video. But first, let's take things simple and just calculate the field integral by itself and see what it actually gives us. We also have to choose the particular theory we are working with. In quantum field theory, we've typically used the free scalar field because that's the easiest field to use, although this generalizes pretty easily to spinors and gauge fields as well. I mean, there's some subtleties with corresponding variables for spinor fields, but anywho, let's use the free scalar field. And the action for the free scalar field is just, so just plug that in there and we get this right over here. This is the path integral for a free scalar field. What we can do to solve this field integral is we can use this thing that we ignore this mustache person. We can use this thing over here that we talked about in the last video. Since before we said that like A was a matrix, and in this case B would be a vector, since we want this to be a scalar. So if X is a vector, B has to be a vector too to get a scalar as a result, since the inner product between vectors is a scalar. And then we would have this over here, and then we can just generalize that. That's a vector, so we'd have this over here, and this 1 over A is just the inverse of the matrix. So yeah, so first of all, like before, we can actually use the DI method. So we have DI, so we take the derivative of partial mu phi, and then the integral of partial mu phi. So this is going to give us the second derivative of this. So this gives us phi. We do this thing, we get phi partial mu phi minus phi, and then the integral of this over here over the volume. And then we have to integrate this as well over the volume, but we assume that this goes to 0 if phi approaches 0 as x approaches infinity. So then this field integral just comes down into being the field integral e, and we can call minus partial mu plus m squared. That can be our operator A. Which remember from before we had that if we get it into this form over here, then we can just read off the solution like this over here. And here we have an integral over here. And the integral is like a sum. And here we have an actual sum. Because the inner product between the vector and a matrix and a vector, that's just going to be a sum, right? So we can write this as the path integral phi e to the I over 2, integral of this, and then phi a phi, where a is an operator, and the solution is going to be the square root of pi I to the n, so pi I to the n, over the determinant. We're actually going to have a 2 pi I. The reason is because we have a 2 in the denominator. Usually, we would have, like, this over here would be e to the minus 1 over a, and then q a q, because the Gaussian integral is actually a negative, technically speaking. Actually, yeah, this should actually be a negative. I don't know why I didn't have a negative there. This should really be a negative. So we'd have to change the I to a minus 1 over I to make it negative. And then if we had like minus 2 over I, then that would correspond to having 2 in the numerator. So that's why we have a 2 there. So we'd have 2 pi I to the n, 2 pi I to the n, then the determinant of a, and then that's pretty much our answer. We don't have any extra terms over here, so this is pretty much our answer. And then we'd have the extra terms from before. We would have like the I m over 2 delta, whatever it was. Well, we can just ignore that now. Let's just call that extra term like b. Okay, so we're gonna have this times b, and then we'd have to take the limit as n approaches infinity, and that's going to give us infinity. This is going to diverge, which isn't really a good thing. So the same thing actually would happen in quantum mechanics. If you use this approach for the free particle, you'd also get a divergence. So that's why the multidimensional Gaussian approach doesn't always work so well. So what we could do is we can instead say, hey, let's add a source term to our functional plus j phi to our action. And what we can do is we call this zj, and then what we could do is we could solve the path integral for this new thing over here. And the path integral for this is going to be the same thing as before, the square root of 2 pi I to the n over the determinant of a times our extra factors of b. And then due to this thing over here, we're going to have this. So b in this case would be j of x. This is a function of x, by the way. And it's going to be an integral because a sum is pretty much an integral in the continuum. So the integral of j over, so an integral over x and y of jx, the inverse of a, and this is our solution. And if you take the limit as n goes to infinity, this still diverges. So what we could do is we could define what's called the normalized generating functional, which is just the normal generating functional zj, but divided by the generated functional without any sources, which means for when j is 0. So if you divide this over here by this problematic term over here, these would cancel out, right? These would all cancel out, leaving us with just this part right over here that does not diverge. Now, technically speaking, if this diverges and this diverges, we can't really just divide them out. If we kind of pretend that it is, we would get a convergent value of e to the minus I, and that would be our answer for the generating functional, the normalized generating functional. So in conclusion, what we did was we solved the path integral for the free scalar field. We saw that it gave us infinity. So what we did was we added a source term j to the mix, and then we defined this thing over here as zj, called the generating functional. Then we divided that by z0, and that will give us just this part over here. And we can notice now that the generating functional of 0 is 1. So we've normalized it to be 1 instead of infinity. Anyways, what we could do now is we have to actually ask what the inverse of a is going to be. So recall that a was defined as minus partial mu plus m squared. So what's the inverse of a differential operator? Before we work out the determinants, but what's the inverse? What does that mean? Say f of x is some function. The inverse of f of x, the inverse is going to be some function that acts on f of x and gives us out x. Now the inverse of an operator, so say we have an operator, let's call it u. The inverse is going to be something that acts on u and gives us the identity. Now the identity in like matrix form is the Kronecker delta ij. Now if we replace the discrete vectors and matrices to actual like continuous functions, u is going to turn into like u of like say x, y, and it's going to give us delta of x minus y. And this over here implies that u is just a Green's function. So basically, what this is saying is that the inverse of the differential operator is just some sort of function that's a Green's function of the differential operator. Or in other words, minus of this over here times the inverse of a is going to be delta of x minus y. And we've actually solved this sort of equation before for the case where we had a plus delta. For the case where it was a plus delta, this was the solution. So if we have a minus delta instead, we're going to have minus for our answer. We can then just distribute the minus to the bottom. That's going to give us, and then this should actually be a minus as well, e to the minus I k mu x mu. I mean, it doesn't actually really depend. It doesn't really matter if this is a plus or a minus, since the delta function is an even function. This just means that our actual answer for the normalized generating functional, that's going to be, so that gives us this over here, and then we can note that I times this integral over here was how we actually defined the Feynman propagator, and we talked about this in the video on propagators. So this means that we can rewrite Zj as, so now we have this over here for the normalized generating functional, and then you can see that I actually snuck in a 1/2 here. The reason is here we had just e raised to the minus ax squared, and then we called a the actual operator. However, if you look at our path integral, we can see that we have like 1/2 over here, and 1/2 is part of the operator that we defined. So here, if we divide by 2, we should divide by 2 here as well, which comes down to dividing by 2 here, and then having a 2 over here. So doing that, we should have a minus 1/2. So this is the final answer for the normalized generating functional. But you guys might be scratching your heads here and saying, what does this even mean, right? Like, what even is J? So basically, this thing by itself, it doesn't really have much meaning. Its role is in what it's useful for. I word that really badly, but basically what we can do here is we can use this formula right over here. We can say that the vacuum expansion value of the time ordered 2-point correlation functions is going to be equal to this over here. And we can see that this contains the normalized generating functional, which we just write as the generating functional, but just know that it's normalized, divided by this thing over here. So that's why it's useful, right? We add the source term, then make everything go to 0 in the end, because we can use it to calculate these endpoint correlation functions. And here I've written a brief justification of this formula over here. We start out with the generating functional, take the derivative with respect to j of x1, and this is going to give us phi of x1 times I. The reason is that j of x is a function, right? So we're taking the derivative of something with respect to a function. Whenever we take the derivatives of functions, the actual out result should depend on that on what the function depends on, if that makes sense. Because if it didn't, then we would just get 0 as a result, right? So that is why we have phi of x1. Same just here, we'd have x2 if you take the derivative with respect to j of x2. And then we can note that we can just divide both sides by I to make the i's go away. And we know that this is just going to be equal to negative I, so negative I. And then we can just divide both sides by z of 0 after taking j equal to 0. And we'd have this over here. And if we define x naught of x1 to be greater than x naught of 2, this over here is going to be time ordered already. And then we can just go ahead and stick those vacuum states in there since it won't change our expression. So that justifies the claim that this is true. And we can easily generalize this to any number of fields if we want to. So this wonky equation is why we actually use the generating functional. We can just put the generating functional into here, and by taking multiple derivatives, we can actually calculate this expression over here. So let's actually do that explicitly for this one over here. So first off, we can take the derivative with respect to x1 here. That's going to be equal to minus 1/2 times the derivative of, you can see here that we can just distribute this derivative inside. So the rule of functional differentiation is that if you have the derivative of jx with respect to jx1, that's going to give us a delta function of x minus x1. If you think of like this as just like x, for example, and this is just y, we basically have dx over dy. And dx over dy is going to be 1 if x equals y, and it's going to be 0 if x is not equal to y. In other words, dx over dy is the delta function of xy. So if you change x to a function and y to a function, that's going to mean we're going to have delta of x minus y. So that's why for function differentiation, we get a delta function when we do that. So that means we are going to be left with delta of x minus x1. This should be the derivative of zj tilde. And we should also be integrating as well. So just using the product rule here, basically the derivative of j of x with respect to j of x1, that's going to give us delta of x minus x1 times d of xy, j of y, delta of y minus x1 for the same reasons as before, and then times z of j. And now we can take the derivative of that again, but with respect to j of x2. So doing that, that's just going to be the derivative then we have to take the derivative of zj with respect to j of x2, but you can actually ignore that part because after we take j to be 0, that integral is not going to contribute anything. So first of all, we can actually break these into two different integrals. We can take the integral over each variable. So the integral over x for the first integral, if you think about it, if you take that, we're going to have delta, or we're actually going to have d of x1 y, delta y minus x2, and then plus integral, and then we're going to have d of x2 y, delta of y minus x2. And the reason is because of the properties of the delta function. If we have the integral of f of x times delta of x minus x1, the answer is just going to be f of x1. So that's why we have that. Now we can take the integral over y. Yeah, this should be delta x1. So we're going to have d of x2 x1 times z of j. Z of j go to 1 since j equals 0. These are equal to each other, since if we flip x1 and x2, we don't really get any difference. So we have 2 times d x1 x2. These cancel out, we get minus d x1 x2. And now what we can do is we can go back up here and we can look at this formula right over here. You see that we have to multiply by negative I squared. Negative I squared is going to be negative 1. So that means we have negative 1 times this whole thing, d minus d x1 x2, So this will cancel out with this negative over here. And then again, dividing it by that, we already did that. So so our answer is dx1, x2 for this thing over here. And that's the Feynman propagator. And we actually calculated this exact same thing in the video about the Feynman propagator, and we found that it was equal to what we have just described over here. So that kind of shows us how we can use the path integral formalism to calculate some things. We can just use this general formula over here to actually calculate these sort of things. And the reason why this is a quantity that we want to calculate is because it's proportional to the matrix element. This is the last video of the path integral for beginner series. Now you are no longer a beginner, you are a pro. See you guys later. Bye.